Today's notes are going to be a little bit different. We're learning about modeling with quadratic functions. So everything that we go over today on this Explore sheet is topics that we've already learned. It's just putting them all together and applying them to real world situations or applying them to word problems. So what I'm going to do is throughout this video, I'm going to briefly talk about some examples, and then I'm just going to ask that you pause the video and you try to do some examples yourself. And I'll have my answers posted in the video, but some of them I just want to make sure you do yourself to make sure you're understanding what we're doing here. For this whole first page, this is all just review of the past 2 units. So for example, number 1 right here, this problem is giving you a function and it's telling you to use the equation of the axis of symmetry to respond to the next 2 questions. For part A, you need to identify the vertex, and for part B, you need to identify the equation of the axis of symmetry. These problems come from Graphing in Standard Form, which was from Unit 4, Lesson 2, Graphing in Standard Form, if you need to refer back to your notes for this. Of course, my work is out here to the side, so as you're doing this yourself, you can double check your work against mine. For numbers 2 and 3, this is solving. You're identifying the zeros. Number 2, you're solving by factoring. Number 3, you're solving using the quadratic formula. These are from the previous unit, Unit 3, Solving Quadratics. And then down here on the 2 graphs you see, it says to identify the zeros graphically and confirm by setting the equation equal to 0 and factoring. So for number 4 and 5, you need to look at the graph. You need to identify where your zeros are. Then you need to take the function that it gives you, set the function equal to 0, factor it, and solve. Once you do that, confirm that your answers graphically and your answers algebraically are the same. So you can do this for both 4 and 5. Before you move on to the next part of the video, please make sure you complete this entire page. Everything on here is used throughout the word problems. We're going to start by reviewing number 6 together. Number 6 is a projectile problem that deals with a trebuchet. A trebuchet is a type of catapult that uses a long arm to throw a projectile, or in other words, it uses a long arm to throw an object, and it throws an object on a path that appears to be a parabola, so something like this. If I were to drop a photo of a trebuchet in and outline its path, we would see something along these lines. So here's a trebuchet. You can see the ball starts down here. So if it starts on the ground, once it hits the ground, it gets launched up. You can see that arrow, it comes, and it's going to land back down on the ground. So something like that, some sort of path similar to what I just drew in here, is what one of these objects creates, or what it does. So we have 3 students that are in a competition, and they must build their trebuchet according to the specs, and they need to launch something as far as they possibly can. So after they conducted the experiments, they followed the quadratic equation y is equal to -1/8 times x squared plus 2x. So this here is our quadratic that we are modeling on the graph here. All right, this one a little bit easier because it's already graphed for you, so you just have to use this graph to answer the problems. And you have to think about this logically. So we have 3 students, they're competing in a competition. They built one of these trebuchets, they launched it. Here is the path of their object, whatever they launched. So the part A asks us, how far does the ball land from the launching point? Okay, well, the ball is launched right here at 0. The x-axis is representing the distance from the launch point. So this ball goes up, comes back down, and it lands right here. According to my graph, it's indicating that this ball landed 16 meters from its launch point, and 16 meters is identified from the number 16 on the x-axis. That is the answer to part A, 16 meters. I know it's meters because it tells me on the x-axis. What is the maximum height of the ball? All right, well, again, the ball starts at 0. This goes up. It hits a maximum height, and then it starts to come back down. So you have to identify on the parabola where the maximum height is. The y-axis represents height. It's labeled right there. It appears to me that the maximum height of this object occurs at 8 meters. Part C. What are the x-coordinates of the points where the ball is on the ground? All right, let's look at our x-axis. Where is this ball on the ground? It's on the ground right here, which is where it starts, and it's on the ground again when it ends. Our x-coordinates are at 0 and at 16. What is the maximum height of the ball 1/4 of the way through its flight? So a quarter of the way through its flight. All right, we know the entire flight happens between 0 and 16. We know that half of the way through the flight must occur at 8. So I'm going to use this graph, I'm just going to label it. Halfway. Halfway through the flight would be the vertex. So a quarter of the way through the flight would occur at 4 meters from its starting point. And just because we're labeling this and because you'll need it in the future, 3/4 of the way through its flight occurs when you're at 12 meters from its starting point. So if the total flight is 16 meters, halfway through the flight occurs at 8, like I just said. A quarter of the way through the flight occurs at 4. I just mentioned that as well. And we can clearly see that at a quarter of the way through the flight, the height of the object is at 6 meters. Just read your x and y axis together. Next, let's look at number 7. Number 7 states that a ball is thrown straight up with an initial velocity of 56 feet per second. The height, h in feet, so your variable of h represents feet, of the ball t seconds after it's thrown, the variable t represents seconds, is given by the formula h of t is equal to 56 times t minus 16 t squared. And for number 7, I also provided you with the graph of that function so you can analyze the graph to answer the questions. Part A says, what is the maximum height? Look at the graph, look at the flight path, identify where this hits its maximum height, and the maximum height is the y-coordinate of the vertex. So the y-coordinate of the vertex is 49. Therefore, max height is 49 feet. I know it's feet because in the description it says the h variable represents the height in feet. Part B says, after how many seconds will the ball return to the ground? Okay, the ball starts at 0. It goes through its path of motion, comes back down, hits the ground at 3.5, and it's time in seconds. So after how many seconds? The answer would be 3.5 seconds. Because you're not always going to have a graph, and this is an Explore worksheet, so if you were working through this by yourself, this next section says to confirm your answer by setting the function equal to 0. I'm just reminding you in these that you can in fact do that. You don't necessarily have to be provided with the graph in order to answer these questions. Yes, the graph is helpful, but you don't need it. That's why I'm marking these little notes on the side. If by chance you don't have a graph, the maximum height is typically the y-coordinate of the vertex. I'm just going back through this now. Part B, how many seconds? That's typically your x-intercepts. Of course, you need to read the problem. It might be specific to the problem, but you can do this without a graph. So for this section where we're confirming our answer to part B by setting the function equal to 0, I am going to take our original function and I'm going to set this function equal to 0. 0 is equal to 56 times t minus 16 times t squared. I don't really like this because it's not in standard form. So I'm going to change it really quick. Standard form has the largest exponent first. I'm going to use the expression 0 equals negative 16 t squared plus 56t. All right, all I did was rearrange the terms. From this equation that's in standard form, I can see that there is a GCF. The GCF is 8. You can factor out negative 8 if you want. Either way, you're going to get the same answer. So let's go ahead and do that. Let's take out a GCF of negative 8. Left over, actually it's negative 8t. Left over would be 2t minus 7. So just to review that, sorry, we are taking out a GCF of negative 8t, left over is 2t minus 7. At this point, you can set each factor equal to 0. You have two linear factors. Linear factors are when you have a factor that has a variable with an exponent of 1. So I can set negative 8t equal to 0. I would divide both sides by negative 8t. Divide both sides by negative 8. T is equal to 0. For the next factor, 2t minus 7 equals 0. 2t is equal to 7. Divide both sides by t by 2. T is equal to 7 over 2. 7 over 2 is 3.5 if you were to write this as a decimal. So either looking at this as a fraction or looking at it as a decimal, t is equal to 0 or 3.5. 0 is your starting point, 3.5 is your ending point. So we just algebraically confirmed that our zeros are the same as what we see on the graph. Part C says, what is the height of the ball after 1 second? You're going to see a lot of problems like this. If I look at the graph, my graph doesn't really help me because all I have is a couple of points labeled and I can't tell what the increments are. So the graph is not helpful for part C. But what we can do is we can substitute t equals 1 because the time in seconds is your x value or your input value. So what I'm going to do is I'm going to take my standard form function, if you're wondering where I got standard form from, it's right here. So I'm taking my standard form function. I am going to substitute the time of 1 second into this function. So I am replacing all t values with 1. When I simplify this, I have negative 16 plus 56. Negative 16 plus 56 is equal to 40. So at 1 second, which is somewhere approximately here, the height of this ball is at approximately, actually it's not approximate, it's an exact answer. We just found an exact answer. The height of the ball is at 40 feet. All right, number 8, let's do this one together. So number 8 also has a graph. I'll read through it in a second, but just remember that the graphs do not have to be provided for you. You can answer all of these questions by just understanding what the projectile path is and understanding what the different parts mean. So for number 8, this says when a gray kangaroo jumps, its path through the air can be modeled by the function negative 0.0267 times x squared plus 0.8x, where x is the kangaroo's horizontal distance traveled in feet and y is the corresponding height in feet. So we have a horizontal distance in feet, that's your x-axis, and we have our corresponding height also in feet, that's your y-axis. Part A says, how high can the kangaroo jump? Okay, looking at the graph, you should be able to easily see that the height of the kangaroo is at 5.93 feet. We can see that. It's the y-coordinate of the vertex. So I can answer my question easily from the graph. Right here, it says to confirm the answer by calculating the y-coordinate of the vertex. I'm asking you to do this because sometimes you won't have the graph and you'll have to actually calculate what that value is. So what we're going to do is we're going to take our original function, which is y equals negative 0.0267 x squared plus 0.8 times x, and we are going to solve for the vertex. Solving for the vertex means that you need to use the equation for x that says negative b divided by 2a is the x-coordinate of your vertex. X equals negative b, which is negative 0.8, divided by 2 times your a value of negative 0.0267. When I type this into the calculator, I have an output of 14.981. Now to solve for the y-coordinate, you're going to substitute x back into the original equation. And once you do that, you're going to solve for y. So you can see wherever I had x in my original equation, I'm replacing it with 14.981. All right, when I simplify for this, I end up with 5.99 for my y value. All right, I found x up here, I found y down here. The question is asking us to confirm our answer by calculating the y-coordinate of the vertex. That's this coordinate, and we just confirmed that. Part B is asking us, what does the x-coordinate of the vertex represent? The x-coordinate of the vertex, this coordinate right here, represents the distance traveled when the kangaroo is at its highest point. I should specifically say the vertical distance. And the last part, part C, is how far can the kangaroo jump? Looking at our graph, the kangaroo starts at 0, goes up, comes down, ends at 29.963 feet. So this kangaroo jumped 29.963 feet. And if you had to calculate that, not looking at a graph, calculating what it is, then you would find the x-intercepts, or the zeros. Obviously, one of them would be at 0. Looking at the graph, one of them would be right here. The other one would be at 29.963. I just went through 3 examples with all the different parts, and now I see this question at the bottom. Do we need a graph to complete the answers on these questions? No, the answer is absolutely not. All you're doing in these parts is you're calculating things you already know. You're calculating the x-intercepts, you're calculating the vertex, you're substituting in values. So you can do all of that just by using the function that the problem gives you. Of course, a graph is very helpful because it cuts down on the time you need to spend calculating stuff, but the graph is not necessary. All right, for 9 and 10 on the next page, as well as the following page, 11 through 14, I'm going to let you work on these by yourself. So before you watch the rest of the video, just go ahead and work on these problems by yourself. Try to work through them. Some of them have a graph, some of them do not. My answer key is on my website, or you can just keep pausing the video as you see my work up here. And we're going to do the last problem, number 15, together. Number 15 is actually comparing 2 different sets of data. So it's 2 rockets launched in the air. One of them is modeled by an equation. One of them is modeled by a graph. And we have to compare the answers for each part. So for part A, it says find the maximum height of each rocket by using the models of their path and which rocket flew higher. Let's start with rocket 1. So for rocket 1, we are only given an equation. The equation is h of t is equal to negative 16 times t squared plus 150 times t plus 1. So to find the maximum height of the rocket, you need to find the y-coordinate of the vertex. In order to do that, we need to fill in the equation x equals negative b divided by 2a. Using the equation above for rocket 1, our value is going to be negative 150, that would be negative b, divided by 2 times a, 2 times negative 16. This simplifies to negative 150 divided by negative 32. So our x value is, I'm going to leave it as a fraction, 150 divided by 32. Then I need to take that value of 150 divided by 32, and we need to substitute it back into the equation to find the y-coordinate of the vertex. I'm going to leave this as a fraction. I am going to just use a calculator, so that's fine if I leave it as a fraction. Just make sure you put parentheses everywhere that I am when you type this into your calculator. So where you see parentheses here, 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 you're going to need parentheses in your calculator or else it's going to give you the wrong answer. Okay, when I simplify this, I get a y value of 352.5625. So that is the maximum height for rocket 1. Again, this is the y-coordinate of the vertex. Rocket 2, a little bit easier. All we have to do here is analyze the graph. So scroll up, look at this graph. We're looking for the maximum height. The vertex occurs right here. The maximum height is at 600 feet. So how did we do this? Again, analyze the graph. Nice and easy for number 2. The directions for part A specifically say, find the maximum height and then which rocket flew higher. So we can answer this question, rocket 2 flew higher. Okay, rocket 2 had a maximum height of 600, rocket 1 only had a maximum height of 352. Part B, which rocket stayed in the air longer? We need to analyze both functions. So to see which rocket stayed in the air the longest for rocket 1, we're going to have to find our x-intercepts, or zeros. To find the x-intercepts of rocket 1, I am going to use the quadratic formula. First I'm going to set my function, which is negative 16 times t squared plus 150t plus 1 equal to 0. And then I'm going to substitute in my a, b, and c values into the quadratic formula. This gives me x equals negative 150, that's my b value, plus or minus the square root 150 squared minus 4 times A, which is negative 16, times C, which is 1. Divide this expression by 2 times negative 16, or 2 times A. So I'm using a calculator right here, but I have negative 150 plus or minus the square root of 22,564 divided by negative 32. Okay, I substitute this into my calculator again, or I type this into my calculator. I have two answers. I have my positive answer. I have my negative answer for the square root. X is equal to negative 0.0067, or X is equal to, I should say approximately, because it's not perfect. X is approximately 9.382. Think about this answer. Can the rocket travel in a negative direction? No, that doesn't make any sense, so we are going to get rid of this answer. So here is our only answer for rocket 1, or how long the rocket stayed in the air. So it starts at whatever height, comes down, ends at 9.32. And this is in time. So this would be 9.382 seconds. Yeah, seconds. For rocket 2, we're going to look at the graph, time in seconds. It appears to me that this graph starts at 0, goes up, comes back down, ends at 12. So that rocket is in the air for 12 seconds, according to the graph. So based on our analysis, using the quadratic formula for rocket 1, analyzing the graph for rocket 2, we can see that rocket 2 was in the air longer. Rocket 2 was in the air for 12 seconds versus rocket 1, which was only in the air for 9.38 seconds. And part C says, what is a reasonable domain and range for each quadratic model? All right, so rocket 1, we never saw the graph for rocket 1, but we have found all this information about rocket 1. So we know where it starts, we know that it hits a maximum height, we know that it comes back down to the ground. So we could sketch a quick graph for rocket 1 based on everything that we've already found. So remember that a rocket cannot travel in negative time and it cannot travel in a negative distance. So it's going to start at 0. Oops. This graph goes up and it comes back down. Its vertex we already found to be x coordinate 150 over 32. And when we substituted that in, our y coordinate was at 352.56 feet. We know that this graph starts a little higher than 0, but starts right here. And it ends right here. This point is at 9.382, comma, 0. That's our x-intercept. So for rocket 1, a reasonable domain, oh, actually, hold on, pause for 1 second. For any problem like this, you are only dealing with the positive quadrant. So you are only dealing with quadrant 1. You will never have anything that goes past 0 in the negative direction on either the x or y axis. So for rocket 1, the domain, it starts here at 0, and it looks like this graph ends at 9.382 seconds. We're going to use square brackets because we include those points. For the range, this graph also starts at 0 because it cannot go negative, and it ends at the vertex, the y-coordinate of the vertex, which is 352.56. Again, we're using square brackets because those points are included. For rocket 2. For rocket 2, let's look at the graph. The domain starts at 0, ends at 12. The range starts at 0, ends at 600. Okay, please let me know if you have any questions on any part of this note sheet. I know a lot of the practice you are completing by yourself, but don't forget that my answers are both here on the video and also posted to my website under the class notes tab. So please check that out. Make sure you understand all of this. Tomorrow's quiz is also counting as a CCA. This is your semester 1 CCA. All right, email me if you need anything.